Well, this may be the most important part of this chapter. 3. Measuring specific latent heat. So, experiment 4C aims at measuring the specific latent heat of fusion of ice. There are a lot of details. Make sure you understand that everything, and please pick up a pen and copy all the notes here. First of all, in this experiment, there are two setups, experimental setup and the control setup. They look alike, but the heater in the control setup is not connected. And yet, you still have to put the heater into the ice because the heater itself is a good conductor. If it is not included in the control setup, then the heat gain from the surroundings would be less. The control setup is used to find the amount of ice melted by the surroundings during the experiment. On the left-hand side is the experimental apparatus. In this case, the ice is melted by the surroundings as well as by the heater here. So, crushed ice is used in both setups because crushed ice are in small pieces and it is usually melting. So we don't have to provide extra energy to increase its temperature to 0 degrees Celsius. Secondly, the very small pieces of ice also ensure good thermal contact between the ice and the heater. In other words, they touch each other well for heat transfer. There is also a steel rule at the neck of both funnels. They are used to avoid the ice dropping directly into the beaker, which will affect the result. So how would it affect the result? Think about it. There will be different masses of water collected in the two beakers. And of course, the mass collected on the left in the experimental setup would be larger. The difference in the mass of water collected is the mass of ice melted by the heater itself. Then we may calculate the specific latent heat of fusion of ice from the geometry reading and the difference in the mass of water in the two beakers. There are a few precautions that we have to be aware of. Other than using crushed ice, other than using melting ice, the heating element of the heaters should be totally immersed in the ice so as to reduce heat loss to the surroundings. Before we start, we have to pack the crushed ice in the two funnels, and we even have to wait until the drip rates are steady and about the same. The drip rates is due to the heat gain from the surroundings. When the heater is switched off, we have to wait a short while also because at that time, the heater is still hotter than the ice and the ice is still melted by the heater. Well, as mentioned before, there should be a wire gauze in the neck of the funnels in order not to let the ice drop directly into any beaker. In this experiment, One possible source of error is the energy loss of the heater to the surroundings. If the heating element is not totally immersed in the ice, or when there is an air gap between the heating element and the ice, energy gain from the surroundings is not a correct answer to explain the source of error in the experiment, because the control setup has already considered the heat gain from the surroundings. Another possible source of error is the different drip rates of the two funnels, especially at the end of the experiment. So eventually, the experimental apparatus will get a lot of water, while the control apparatus will get less. The difference of the water collected is due to the heat from the heater, and that is the amount of ice melted by the heater. And so we may make use of this M2 minus M1 to find the specific latent heat of fusion of ice. Spend some time, read example 4 below. On this page, you can see writing practice. In the above experiment, there is a control setup. Without the control setup, then the amount of water collected would be larger than the mass of ice melted by the heater. So when we apply the formula, then we may have an overestimated mass of ice melted. Then we may calculate a smaller latent heat of fusion than the standard value. So what about these two cases? Read the question and try to formulate your answer. The last one is experiment 4D, which is an experiment to find the specific latent heat of vaporization of water. In this setup, you can see there is no lid for the container. Why? Because in this case, you have to let the steam escape. On the other hand, when the steam tries to escape, some of the steam also condenses on the cooler part of the heater, and then they drips back to the container. In other words, they don't go away. The mass of the water does not decrease as it should be. How would it affect the value of latent heat of vaporization? This setup is a bit simpler than the one for latent heat of fusion, and yet there are some precautions, such as we have to wait until the water becomes steady before we take the final reading of the electronic balance. Because when the heater is turned off, the heater is still hotter than the water, and in this case, the heating continues, the evaporations continuous, and then it takes some time until the heater and the water to reach thermal equilibrium. At that time, then we may take the reading of the electronic balance. Another standard precaution is to insert the heating element of the heater totally in water, so as to reduce the heat loss to surroundings and also protect the heater, or else it may overheat. One important source of error is the steam condensing on the cooler part of the heater and then drips back to the cup. And so the change in the balance reading would be smaller than expected, and the calculated latent heat of vaporization becomes larger than the standard value. Now, take a look of example 5, and it talks about a old type of kilowatt hour meter in which you have to count the number of revolutions. It says that there would be 600 revolutions for each kilowatt hour of energy consumed. So what does that mean? 1 kilowatt hour is indeed 3,600,000 joules of energy. In other words, 3.6 million joules of energy. If there are altogether 600 revolutions, then each revolution means 6,000 joules of energy. In this experiment, it says that there are altogether 41 revolutions counted, and so we may use this 41 together with 6,000 joules per revolution to find the amount of energy absorbed as latent heat of vaporization. Well, Jimmy was silly. He says we may add a lead, and of course it is wrong. Why? Turn to the next page and find the answer. So this is the solution of the example. Spend some time and see if you can also write quality answers like this as in part C. For the lower part of the page is writing practice, and in this case, it talks about the latent heat of vaporization of water again. Well, how would the calculated latent heat of vaporization be affected if some water splashes out of the cup? Think about it. Try this question yourself and see if you are able to write quality answers as those above. Lastly, try the quick check question here before you move on to the next video.